That is what, supposing I say y is g of x, and this is the advantage of doing transformations before expectations, because this is no longer new to you. If I hit you on the head, if I put this, let us say immediately after defining x, you don't know what the hell is g of x, right? Now you know, you don't have to worry about g of x, it's yet just another random variable, and you have done enough examples and problems to understand what that, right, how to handle this. Now to find the mean E of y, do I have to go through the PDF route, that is find fy? Answer is no. We don't need yes, you can always do it, right? There's a long route. You can touch your nose either by doing it like this or like this, right? But the thing to do is, so unless you need the PDF, or of the derived quantity y, you don't have to compute it. Certainly you don't have to compute the PDF, the output PDF of this transformation to simply find this mean value. Instead, what we have what is called lotus. Has anyone seen the expansion to this term? This is a very nice acronym, and I've seen it used in so many places that I'm sure it's there in Google search also. I have not done it. The expansion of lotus in this case happens to be law of the unconscious statistician. Main thing is unconscious statistician. You unconsciously you do it. What do you think? How do you think I should go about finding E of g of x? I just substitute what in place of x. What do? I put g of x. Unconscious. I do it without even a second thought, isn't it? I don't even need y. I can just say e g of x. I don't even have to capture the output of g of x as some y, right? I just write e of g of x as what? Integral or sum over omega x in case this is continuous. So I am assuming, of course, that I am assuming that this g is reasonably well behaved, which allows y to be purely continuous and this integral to be written, and of course it's a summation for this. In fact, I think is really easy to understand, the discrete case, because if x is discrete, then y of g of x is also discrete, and the PMF, if you go back, you can easily interpret this using PMFs. Let me put P here. You can easily, right, if you, let's say it's a one-to-one transformation, right? You want y into Py of y, but what is y? It's one of the values of g of x, and Py is P of g of x, Py of g of x is equal to Px of x, and there's a one-to-one transformation from x to g of x by right, conservation of probability or transfer of probability. And even if 2 or 3 things map to the same g of x, this summation will take care of that. This g of x will be common, right? If there are 2 values of x mapping to the same g of x, right? The g of x will be common, and this summation will clearly be exactly equal to sigma y Py. But in any case, remember lotus, you do this even without giving it a second thought. It's so as natural as that. Do you agree or not? Even without my saying it, you people said the answer, right? At least some of these people said. They're a little more vocal than folks out there. But let me also ask you: you agree? It's almost a simple extension. Anyway, take a minute to appreciate it. Now, where is this mod of x coming? I wrote E of mod of x. What g of x did I use for that mod of x? Just mod x itself. If I use y equals mod x, I would get exactly the same thing here. So if I want to put a mod sign here, that is E of mod x, all I have to consider is a function mod x. That would exactly give me mod x sigma of mod x px or integral mod x fx, and that has to be nothing but this E of mod x. So which this explains E of mod x. Again these integrals are not guaranteed to exist, very clear. If E of x itself does not exist, there is no guarantee that E of g of x for some arbitrary g is again going to exist. I can have an exponentially increasing g or something. So obviously you can cook up any g, and these integrals and summations will be finite only if omega x is a finite interval or a finite collection of points, right. So then you do not have to worry, but as long as you say right either plus infinity, right, it goes up to plus infinity or the entire real line, then these integrals cannot be guaranteed to exist. So again, what is a test? What is the implicit assumption we are saying? If you are saying that this is finite, that means that you have ensured that by putting a mod around g of x, the sum or the integral converges to some finite value, right. Only if that is finite, then we say that E of g of x is given by this expression. Otherwise you say E of g of x does not exist at all. Okay. What is the use of this g of x? Come on, you tell me, beyond E of mod x. What is the next important okay, you have understood the mean value. Why did I have to introduce all this E of g of x now apart from mod x? What is the statistic that your next statistic of mod x that you care about? The variance. But before the variance, or study the variance, I need one more basic quantity, which is E of x squared. So please wake up and right, I want you to tell me that you want, right, the next thing after E of x is E of x squared, right. So E of x squared is, if E of x is the mean value, E of x squared is called the mean squared value, mean of the square. I am not sure if it's a D here or not, but means let me not, I do not think mean square value, let me just say. This is not in general the variance, right, but it's for the variance we have to do more work. We will come to this variance maybe tomorrow's class, not today, but E of x squared is just a special case of E of g of x. And in any case, for a real dynamic variable, mod x squared is the same as mod x whole squared, so you do not have to worry about either the integral will straight away diverge or converge. That itself tells you whether E of x squared exists or not, right. You do not have to do any special test for this, okay. Alright, so that is, so what I will do in today's class is to wind up by looking at some properties of the expectation operator, then we will study the variance tomorrow. Let me list out some simple properties of the expectation, which we can do at this point. This is going to be an incomplete list, right. We will keep expanding on this as we go along. So just with whatever we have studied in half an hour today, what properties can we write? Let me not list them. Expected value of a constant is equal to the constant, first of all. It's very important. This is a case of what? G of x equal to c. This always exists if c is finite. You do not care about even the E of x itself might not exist, but E of c always exists, because sum of a probability distribution or integral of a probability distribution is 1. That is, without that you do not have a probability distribution. So therefore E of c is always c. Okay. So then what is E of cx? C into E of x, right. Again this requires Ex to exist, but let me not keep on again sounding a broken record each time, right. If we write E of x, we are assuming that there is no problem with that number. So this should not be any should not right pose any problem to you. All you have to do is stick in place. Just remember this. Wherever right whatever comes here you put here, and obviously if Cx you have, C will come out and you will be left with the standard integral for E of x. Okay. Then the important linearity property. This is also a linearity property, but let me write the more general linearity. E of, let us say if I have two functions alpha g1x plus alpha 2 or c1 plus c2 whatever, what right, what is this, right. Okay. So it's all very easy right. Then E of x for non-negative random variables, which means what, x does not take negative values. E of x, if it exists, has to be at least more than 0, it cannot be negative. These now up to here it is all equality. Now we are going to look at some bounds. For non-negative random variable, obviously there is no negative term in the sum or integral, and the resulting thing has to be positive. If you say it is non-negative and somehow E of x turns out to be 0, then that means x must be 0 with probability 1, x is degenerate, it is not random at all. That is a very no, it is an exceptional case, so let me not. Then if g of x is positive, this is right. Okay, so let g of x be positive for x in omega x, capital omega x. This is of course like x squared, which is positive for all, non-negative for all x, but it doesn't have, you don't have to consider x squared in general. You can look at just any g of x which is positive for omega x alone. Then E of g of x must be also be non-negative. This implies that E of, so which e.g. let me write at the bottom here, E of x squared, remember this E of x squared can never be negative. No matter what distribution you have for x. Okay, so I think we will stop here for today, and so this is by no means a complete list, we will expand it as we go along.